Okay, we're going to do higher level polynomials, and there's a bunch of theorems that come with this. So I have the definitions to start with, but I'll get to each of those singly. Okay, let's start off with just what a polynomial is. Right now I have a polynomial that has 1, 2, 3, 4, 5 terms. So because there's 5 terms, we call it a polynomial. If there's just one term, we call it a monomial. If there's just 2 terms, it's called a binomial. If there's 3 terms, it's called a trinomial. But if there's more than 3 terms, it gets a generic name of polynomial. So these are just polynomials. Okay. The coefficient of each term. This is a 7. This is a -7. This has a 1. This has a -6, and this has a 9. The degree of each term. To find the degree, you add up how many variables you have in each term. So this has 2 x's and 3 y's, so this has a degree of 5, 4 and 2 degree of 6, 1 and 1 a degree of 1, 2, 0. Okay, so I have degrees of each term 5, 6, 1, 2, and 0. The degree of the polynomial. The degree of the polynomial is always the highest degree. Whichever term has the highest degree is the degree of the polynomial. So my degree is 6. The leading term is whichever one had the 6 with it. So it's -17 x to the 4th y squared is my leading term, and my leading coefficient is -17. Just so you know how polynomials work. So again, coefficients 8, -7, -1, -5, 11. Degree of this one is 9, 5, 3, 1, 0. So 9, 5, 3, 1, 0 is the degree of each term. The degree of polynomial is the highest degree of the terms, so it's 9. So the leading term would be 8x to the 4th y to the 5th. And the leading coefficient would be 8. Okay, this should all be reviewed for you, but if it's not, there you go. That tells you how to find the degree of each term. Okay, multiplicities of zeros. It tells you how many zeros you have, and remember, zeros are x-intercepts, or your roots. And you find your multiplicity by looking at your exponents. So there are 2 x's here. If I FOILed this, I'd get x squared. This, if I FOILed it, there'd be 7 x's, and this would have 1. So I have 2, 7, and 1, 2, 9, 10. My multiplicity is 10. That means I could have 10 zeros. Your multiplicity tells you how many real zeros you can have, how many zeros you can have. Okay, so when you're looking at that, or how many roots you can have, so multiplicity is something that you want to look at. Now, if you want to write your own, remember, you have, this has a multiplicity of 2 at x equals -2. So x, bring that over, plus 2 to the multiplicity of 2. X equals 0. So bring that over, I still have x to the multiplicity of 4. And x equals 1, bring that over, x minus 1 to the 1. So my equation would be y is equal to, and I'd probably put the x to the 4th first, because that's my single, x to the 4th, x plus 2 squared, x minus 1. And I might actually do it in order of x minus 1 and x plus 2 squared. Does it really matter? No. But there are 7. 4, 6, 7. Okay, so this x equals -2. That's where it crosses at. And x equals 1. This has a single root. This has a double root. Double roots always touch and turn. Okay. This has a multiplicity of 3, which means it starts at the bottom, ends at the top. So it's going to come up somewhere at the bottom, go in, turn, touch, and go back up again. Now remember, we're just sketching. see how close we are. X plus 2. I mean, we can get to the point where we can graph this using all our rules and theorems pretty darn close. But right now, we're just getting the idea of why this all works the way it does. See? Not too bad. Okay, so on the next one, I do not have this in the form that I want it for multiplicity. So the first thing I'm going to do is see if I can factor anything. So I can take out a 2x squared, and I'm left with x squared minus 4. That becomes 2x squared, x plus 2, x minus 2. So 2x squared equals 0, so x squared equals 0, so x is equal to 0, and it's a double root, so it's going to touch and turn there. X is equal to negative 2, x is equal to positive 2. Even, positive, starts up, ends up. So it comes down, touches, turns, comes back up again. Anytime you have a double root, an even root, it's going to touch and turn. Anytime you have an odd number of multiplicity, it's going to go through. So even touches and turns, just like it did here, and odd goes through. So let's see what we got. 2x to the 4th power minus 8x squared. Not too bad. So we can learn a lot about graphs without actually doing a lot, just knowing the theorems that go with it. Okay, we should already know how to divide polynomials by synthetic, but we need that because once we find the roots, we can break it down further using the roots. Okay, so if I have a monomial divided by a monomial, one term by one term, I do it just like a fraction. 24 and 18 both have 6 in it, so it's 4 over 3. And I have 5 z's on the top and 3 z's on the bottom, so I have 2 z's on the top. Okay, that's how I divide monomials. If I have anything over a monomial, what I do is I split it up into separate terms, just in case I get fractions somewhere along the line. So I get 4p squared plus 5p plus 1. Long division, you put the dividend inside, divisor on the outside, and you want to make this look like this. So I need a 4x. 4x times x is 4x squared. 4x times 3 is 12x. Then you subtract, so you change a sign, change a sign. This first term should always drop out. And I have negative 5x plus 3. I make this look like this, so I put negative 5. Negative 5 times x is negative 5x. Negative 5 times 3 is negative 15. Change the sign because I'm subtracting. 18. That's my remainder. So it's plus 18 over x plus 3. Now remember, when we talk about isotopes and we have to do division, we never take the remainder in effect for an isotope, for the oblique isotope. But here we have to take it into effect because we're not doing isotopes, we're doing straight division. For synthetic division, make an upside down L. We take the coefficient of the dividends, 4, 7, and 3. We set the divisor equal to 0 and put that on the outside. Bring down your first number, multiply negative 12, add negative 5, multiply 15, add 18. Every time you divide, you take one power off. I started with x squared, so this will be x, this will be nothing, and this will be my remainder of x plus 3. And like I said, this should be a review for you if you took 051 or the previous course, and if you didn't, I'm hoping a quick review will help. So long division, divisor inside, dividend inside, divisor on the outside. make this look like this. So 2x squared multiply 6x cubed plus 4x squared. Change the sign, gone. Negative 15x squared, bring down your next term, negative 7x. Make this look like this, negative 5x, negative 15x squared minus 10x. Change the sign, gone. 3x, bring down your next term, 2. Make 3x look like 3x plus 1. So 3x plus 2, change the sign, 0. Divided. No remainder. Synthetic, 6, negative 11, negative 7, 2. Don't forget your negative signs. If a subtraction is going to be negative, set this equal to 0. Negative 2/3. Bring down your 6, multiply, negative 4, add, negative 15, multiply, 10, add, 3, multiply, negative 2, 0. Now notice these are all divisible by 3. On synthetic division, you have to divide by the GCF if at the end they have a GCF. So I'm going to have to divide it. If there's a remainder, you don't divide the remainder by the GCF, only the initial numbers that are not in the remainder. So as I start with x cubed, so this will be x squared, x and nothing, divide by 3, divide by 3, divide by 3, 2x squared minus 5x plus 1. And then I get the exact same thing as the other one. Now, why do you have to know long division and synthetic division? Because in long division, sometimes it's easier to use long division than synthetic division. Like in this next one, I have 2x to the 4th minus x cubed minus 3x squared plus 13x minus 4. Now please remember, if this x cubed didn't exist, I would have to put a 0x cubed in there. I have to have a space for each decreasing x. So if it's not there, you have to put a 0, that x. On the outside, I put x squared minus 2. X squared to 2x to the 4th is 2x squared. Multiply. Multiply. Now, I'm not going to put it here because it's an x squared. I'm going to put it here. Change the sign, gone. Bring this down. Add this. Bring my next number down. So I need to make this look like this. So it's negative x cubed plus 2 plus 2x. Change the sign, gone. X squared plus 11x minus 4. Make this look like this, so plus 1. So x squared minus 2. Change the sign. Gives me 11x minus 2 plus 11x minus 2 over x squared minus 2. So you say, well, okay, let's do synthetic. So I start out with 2, negative 1, negative 3, 13, and 4. I set this equal to 0. I get x squared equals 2, square rooted x is equal plus or minus the square root of 2. So you'd have to do the square root of 2 and then do negative square root of 2. 1, it's 2 steps, which we're going to be doing later. But the biggest problem is we're going to be multiplying everything with the square roots. So you can make more mistakes multiplying with the square roots than if you could just do long division. So if you're ever using something and you're dividing by something that is more than a multiplicity of 1, this one is 2, it's best to use long division. I am going to show you how to do the other one in a little bit, but not with the square root of 2. Okay, so that was a review for us to get to this point. The factor theorem says that the number c is a 0, the polynomial function y equals p of x, if and only if x minus c is a factor of a polynomial. In other words, it means we can factor to solve our zeros. And we've already been doing that previously. So I take this and I factor it. 1 and 6, 2 and 3, subtract for -1. So it's -3 plus 2. Set each of them equal to 0. Solve. And it gives us our roots. So one way of finding our roots, or our x-intercepts, or our zeros, which are all the same thing, is by factoring. So both 3 and -2 are zeros of the function. And that's called the factor theorem. Just means that you can factor. The fundamental theorem of algebra says that a polynomial's function of positive degree when y equals p of n has at least one zero in the set of complex numbers. So if you have at least one real zero in the complex number, if it's a positive degree. In other words, it tells you how many zeros you have. Okay, we have another theorem. This is filled with theorems. This is the remainder theorem, and the remainder theorem is a way of using synthetic division to find the answer without plugging something in. Normally, we would take 2 and plug it in here and get 2 cubed minus 4 times 2 squared plus 5 times 2 plus 3. 8 minus 16 plus 10 plus 3. -8 plus 10 plus 3. 2 plus 3. 5. Notice what your remainder was. 5. The remainder theorem says that instead of plugging the number in for x, if you do a synthetic division, whatever your remainder is your answer. And it also practices your synthetic division. So I took 1, -4, 5, and 3, placed them in here. Set this equal to 0, so x equals 2. Brought it down, multiplied, put it up, add. Multiply, put it up, add. Multiply, put it up, add. Answer. So instead of plugging it in, we're going to use the remainder theorem. So let's try it on this one. 2, -3, -11, 6. We're going to use 3. Bring it down, multiply, put it up, add. Multiply, put it up, add. Multiply, put it up, add. Answer, 0. -2, -3, -11, 6, -2. Bring it down, multiply, put it up. Multiply, put it up. Multiply, put it up. 0. One half. 2, -3, -11, 6. Bring it down, multiply, put it up. Multiply, put it up. Multiply, put it up. 0. Now, why would we do it so that they were all zeros? Well, what that means is they are zeros of that function, meaning that I'm looking for 3 roots, and my roots are 3, -2 and a half. And how do I know they're 3, -2 and a half? Because when you do a synthetic division and you end up with no remainder, you found a 0. So we were using remainder theorem to prove that they were zeros. So if you end up with a 0 as your answer, that means that they are your zeros, or your x-intercepts, your roots, and therefore you know where it crosses the x-intercept axis at. So let's try this one. 1, -13, -7, 10. I'm actually going to start it higher. 1, -13, -7, 10. And I'm going to start with x equals 3 and x equals -2. It doesn't matter which one I start with. I'm just going to start the first one, 3. They're telling me it's a root, so it better come out 0 at the end. So bring down 1, multiply 3, -10. Multiply, -30. Well, that's definitely not going to work. Well, they're definitely not roots. Negative 37. Bring down your 1. Put it up. Negative 10. Put it up. Negative 37. Negative 111. That's definitely not a root. Not a very good problem there. I apparently typed it wrong. Well, let's try this our way then. Let's say I don't know what my roots are. Let's hope this one has a root. I could go to the calculator and go to y equals. I can put in x raised to the 4th power minus 13x squared minus 7x plus 10. And hopefully I didn't type the whole thing in wrong. Hit second graph and see if I can find any zeros. I can't. That means I typed the whole thing in wrong. Let me find you a new one, which will probably be on your new paper. Okay, let's try this again with the new equation. Okay, this is to the 4th power. And on quadratics, we can factor. Okay, that's not a problem. But when we have something higher than a power of 2, a multiplicity higher than 2, we're going to need to break it down and get it down to a multiplicity of 2 so that we can either use the quadratic equation or factor. At this point right now, I can't use the quadratic equation or factor. So I have to find some of the roots to start with. So they're telling me, I'm telling you now since I went back and redid it, x is equal to negative 4 should be a root, and x equals 2 should be a root. So I'm going to take and I'm going to do a long division using 2, negative 3, negative 27, 62, negative 24, and I'm going to start with negative 4. Bring down, multiply, put up. Negative 11. Bring down, multiply, put up 44, subtract 17, multiply negative 68, subtract 6, multiply negative 6, multiply 24, 0. It is a root. See, when we get the 0, it's a root. And we're now down to, remember, we started with the power of 4, now we're down to a power of 3. So I'm going to just continue my division from where I'm at. And I'm going to do 2. Bring down, multiply, put up. Negative 7, multiply, put up. 3, multiply, put up. 0. Now I'm down to a multiplicity of 2. So I can write this as 2x squared minus 7x plus 3. And now I have the possibilities of finding the other two roots by either factoring or doing the quadratic equation. This does factor. So I'm going to slide this over. I'm going to get x minus 6, x minus 1 equals 0. I slid, so I have to divide. So x minus 3 equals 0, so x is 3, is a root. And x minus 1/2 equals 0, so x equals 1/2. I have 1 root, 2 roots, 3 roots, 4 roots, and I found all my roots. Now remember, when I have a polynomial that's higher than a multiplicity of 2, there's some way I have to get it down to a multiplicity of 2. So if I can find some of the roots, I can divide it out, get it down to a quadratic, and then with that quadratic, I can either do the quadratic equation or factor. Okay, some other ways to tell what's happening with this graph and where the roots are, because how am I going to find all these roots? How did I find negative 4 and 2? Well, they gave them to me. Well, how do I find them? Well, what you do is you take your, it's called the rational zero theorem. And what you do is you organize your equation from the highest to the lowest exponent, so from the leading coefficient down. Then you take all the factors of the constant term, the term in the back, the plus and minus versions of them, and all the factors of the leading coefficient, which they call the Q, and then you put P over Q, cross out any duplicates, and then they are your possible roots. Wow, a lot of words for that, huh? Okay, this is what it means. This is lined up from the highest x to the lowest x, 4, 3, 2, 1, none. And this is, whoops, wrong thing. It's P over Q. Here's my P, here's my Q. So I did all the factors of 9. So 1 and 9, 3 and 3. So plus or minus 1, plus or minus 3, plus or minus 9. There's my factors of 9. And then I do all the factors of 2, 1 and 2, plus or minus 1, plus or minus 2. And then I set them up as fractions. Plus 1 over plus 1, plus 1 over minus 1, so it can be plus or minus 1. 1 over 2, plus or minus a half. 3 over 1, 3 over 1. 3 over 2, 3 halves. 9 over 1, 9 over 2. So these are all the possible things I can use to do synthetic division to find the roots. You think, well, think here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 of them and there's 4 roots. Seems like a lot, huh? So they started off with positive 1. It came out to negative 16, so that's not a root. Then they did a synthetic division with negative 1. It came out as 0, so the 0 is a root. Then they did positive 1/2 root, because it came out as 0. Then they did negative 1/2, not a root because it came out 35/4. Then they did 3 root. Okay, so we have 1, 2, 3 roots so far. Then you continue until you find all of them. Then they did negative 3, became a root. So you have roots of negative 3, negative 1, 1/2, and 3. Seems like a lot of work, doesn't it? This is what I'm going to expect you to do, okay? 1, I expect you to be able to find out all the possibilities. Then 2, I'm going to let you pick up your calculator, put in the equation. Let me see if I can fit it in here somewhere. Uh, 2x to the 4th power plus x to the 3rd power minus 19x squared minus 9x plus 9. I'm going to let you go to the graph. And I had it on 0.5, so I'm going to change that. Start at 0 and count by 1s. Well, I need 0.5s because I have a half there. I have halves and 1 1/2, so I'm going to need to count by 0.5s. I'm going to find some zeros. Okay, I have a 0 at 3, so I could do 3 and I could prove it. Okay, so do 3 and prove it right here. I have a 0 at 0.5, a half. Prove it. I have a 0 at negative 1. Prove it. And I have a 0 at negative 3. Prove it. Or, better yet, you can prove it by doing it this way. 2, 1, negative 19, negative 9, 9. First one we found was 3. What we found on the calculator. So 2, 6, 7, 21, 2, 6, negative 3, negative 9. Proves it. And let's go on to the next one. The next one that we found was a half. 1, 8, 4, 6, 3, 0. Proves it. Then we found negative 1. Negative 2, 6, negative 6. Proves it. Then we found 3. 2, 6, -3, -6, 0. Proves it. And that's a way of proving all of them. So I'm going to let you use your calculator to try to figure out which ones to use, but I expect you to be able to factor the p, which is your constant term, and factor your q, which is your leading coefficient, and put down all the possibilities, so you at least know what you're looking for. Okay, so p, plus or minus 1, plus or minus 3. Q is plus or minus 1. So it's 1 over 1, plus or minus, and 3 over 1, plus or minus. There's your possible zeros. So 1, 3, -1, -3. Let's try 1. 1, 1, 4, 4, 3, 3, 0. So 1 works. And remember, we can look up to 3 of them. Okay, so 1's a 0, so x equals 1 is a 0. Now I don't know what the next 0 is, so I can't keep going. I could keep going, but then I'll have to go back or erase. So if you want me to keep going, that's fine, or I should start back over again and try it separately if I'm just looking for the zeros. So 1, 3, -1, -3, I'll try -1. 1, -1. 2, -2, -3, 3, 0. So x equals -1. 1, 3, -1, -3, try 3. 3, 9, means 6, apparently can't add. 18, 17, way off, no. Let's try -3. 1, 3, -1, -3. 1, -3, 0, 0, -1, 3, 0. So x equals -3. Remember, I told you you can use your calculator. So if we took our calculator to see which ones actually work, now you have to be able to state this to me, because I want you to understand how you find them if you don't have a graphing calculator. Y equals x to the 3rd power plus 3x squared minus x minus 3. Second graph. So I have a 0, -3, a -1, 0. No, 1, 0. Okay, so good for us. Okay, in order, what's your constant? Well, you don't see one, right? Well, that's because I have to pull out the x squared first. I'm going to pull out a -2x squared and get x squared plus 4x plus 1. Now, I can have up to 4 real zeros. And since I didn't have a constant to start with, I can change. And you see, when I factored it, I'm down to a quadratic. So I have -x squared equals 0, divided by -1. X squared equals 0. X equals 0. And this is a double root. And this, I can do the quadratic one. -4 plus or minus the square root of 4 squared minus 4 times 1 times 1 all over 2 times 1. Now remember, what we're doing is we're trying to find the roots. This one doesn't follow the same format because there is no constant. So I have -4 plus or minus the square root of 12 over 2. 4 and 2, 4 and 3, 2 and 2, -4 over 2 plus or minus 2 square root of 3 over 2, -2 plus or minus the square root of 3. So here are my irrational roots. Here is my double root. So even though I want it to fall into this theorem that I'm having, sometimes it doesn't, so I have to go back to what I know as well. Okay, here's my p, and this does fall in. 1 and 8, 2 and 4, plus or minus, plus or minus, plus or minus, plus or minus. We're going to have a lot. This is 1. So it's plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. We can start trying, or we can pick up our calculator, graph it, x cubed. That's one reason why we got this graphing calculator, so that we can use it. But if we don't have the graphing calculator, we would do it the other way by doing the long division on it. And finding out where it comes out as 0. So we got a negative 2. X equals negative 2 is 1. X equals 2 is 1. And negative 1. Neither of those work. We already got those. Positive 4, negative 4, positive 8, negative 8. The negative 4 and negative 8 doesn't work. Positive 4, positive 8 doesn't work. So there are 2. One's probably a double. Has to be a double. Because all irrational numbers come with a plus and minus, and all imaginaries come with a plus and minus. A new theorem we're going to be coming up soon with. And let's see, we'll graph it and see what we get. See how this one right here is a double? Right here is a double, and negative 2. That's why we couldn't find the third one. The next one, I don't have a constant, so I can't use the same thing, so I pull out my x squared. Get x squared minus 4, so I get x squared equals 0, so x is 0. I have a double rooted 0 because of the multiplicity. And then this is x minus 2 and x plus 2. So x is 2 and x is negative 2. So I don't always have to use that theorem, even if I am using a higher polynomial. I have to know everything that I know to go back and look at it. Let's look at the graph. X raised to the 4th power minus 4x squared. Graph it. Don't put that in right. Oh, didn't. Look at that. I put a 2 instead of squared. Whew. Now see the double root here at 0, crosses at 2, negative 2 and 2. Okay, the number of roots of a polynomial equation. Multiplicity tells you how many roots that you can have. Okay, so if I have a multiplicity of 7, that means I can have up to 7 roots. Doesn't mean I have 7 roots, it just means I can have up to 7 roots. The end root theorem says if a polynomial equation with real or complex coefficients and the positive degree of n, then a multiplicity is considered 0. So in this one here, finding the multiplicity, I have 2, 7, 9, 10. So this has a multiplicity of 10, which means I can have up to 10 roots. Okay, some of them might be imaginary roots. So I can have up to 10 real roots. If they're imaginary roots, they don't count as real roots, so that's why you might not get your 10. But it tells us how many we should be looking for. Okay, so this is x equals negative 1, 2x minus 3 equals 0, so 2x equals 3, so x equals 3/2. So I have, it's supposed to be 1, 2, 3 roots. This is 1, this is a double root. So there are my other 2. Where are my roots here? Negative 3. So I have an x equals negative 3. I have an x equals 0. And I have an x equals 3. So x equals negative 3. Bring it over. X plus 3. X equals 0. Bring it over. X. X equals 3. Bring it over. X minus 3. So x plus 3, x minus 3. And none of them are double roots because none of them touch and turn. Okay, I need to find the polynomial with a degree of 7 who has these following zeros. Negative 2, so x equals negative 2, bring it over. X plus 2, multiplicity 2. X equals 0, bring it over, multiplicity of 4. And x minus x equals 1, bring it over, x minus 1 with a multiplicity of 1. So x to the 4th times x plus 2 squared times x minus 1. And this should be a review. In fact, I know I did these problems with you before in a different unit. I just want to make sure that you understand the multiplicity tells you how many possible real roots you can have. Okay, find all the zeros of the following functions. Okay, this one. I can't do the constant and the leading coefficient because there is no constant, but I can pull out a 6x cubed, and I'm left with x squared plus 4. Two x cubed equals 0. Means 6x cubed equals 0. X cubed equals 0. X cubed mean x is 0. So I have 3 roots at 0. So there's 3 of my 5 roots. And my other root is x squared plus 4 equals 0. So x squared equals negative 4 square rooted. X is equal to plus or minus 2i. I have 2 imaginary roots. So I have 3 real and 2 imaginary for a total of 5. And you're going to find out in one of the theorems coming up soon that if imaginary roots always come in pairs. So if you have one imaginary root, you have to have a second one. X equals 3. X equals negative 14. This is a double root. And this is happening 5 times. So I have 5, 6, 7, my 7 roots. Sketching the polynomial. Going back to everything we know, x is equal to negative 2 is a root, x is equal to 1 is a root. Negative 2, 1 has a multiplicity of 3, which means one's going to start up and one's going to start down, or down and up. It's positive in the front, so it's down and up. 2, negative 2 is a single root, so you're going through it. 1 is a double root, so you're going to touch it and turn it. Sketched. Okay, conjugate pairs theorem. All real coefficients, polynomial with a real coefficient, and the complex number a plus bi as a root will also have a minus bi as a root. They come in pairs. Imaginary numbers, complex roots come in pairs. So here they told me I had a root of 2 and 1 minus I. So I do x equals 2, so x minus 2. And I do x is equal to 1 minus I. So it's x minus 1 plus I. And I have x equals 1 plus I. So that's x minus 1 minus I. You can only multiply 2 things at one time. And if I put a plus on here, plus I, and this is x minus 1 plus I and x minus 1 minus I have conjugates. This is a conjugate of this. So x minus 1 times x minus 1 is x minus 1 squared. Middles will drop out. I times negative I is negative I squared. And I have x minus 2. I have to FOIL this. X minus 1 times x minus 1 gives me x squared minus 2x plus 1 minus I squared times x minus 2. And what's I squared? Negative 1. So it changes this to positive 1. So I have x minus 2 times x squared minus 2x plus 2. FOIL or put it in the box. I'm going to put it in the box to show you. Just to keep everything straight. X cubed, negative 2x squared, negative 2x squared, 4x, 2x, negative 4. X cubed minus 4x squared plus 6x minus 4. So we're going to try one, because that one was already done and we could have cheated. Okay, x equals 3, so x minus 3. X equals negative I, so x is also equal to positive I. Remember, conjugate theorem says if it's one, it's the other one. So x plus I, x minus I. These two are conjugates, so x squared minus I squared, because the middles will drop out. This is plus 1. So I have x minus 3 times x squared plus 1. X cubed plus x minus 3x squared minus 3. X cubed minus 3x squared plus x minus 3. So, anytime I have one imaginary, I have a second imaginary. Even if they don't give it to me, I know I have it. That's what the conjugate pair theorem says. I told you this was a theorem chapter. Lesson anyway. Okay, Descartes' rule of signs. Descartes' rule of signs tell you how many real, positive real, and negative real solutions you have by looking at the changing of signs. So the first thing you do is line them up from the greatest to the smallest in powers. Then you look at where the signs change. Positive to positive, no change. Positive and negative, one change. Negative and negative, no change. Negative and negative, no change. Negative to positive, one change. Positive and negative, one change. That allows me to have 3 possible positive real roots. Another thing just to show us how to figure out how many roots that we could possibly have. Then what you do for the negative roots is you put in negative x. So every time I put in a negative x, all my odd exponents will turn opposite sign. So I had positive 7x, now it's negative 7x. The evens will stay the same. Stays the same, stays the same. Look, changes, same, same, changes, same, changes, nothing. Same. So look, now negative, same, same, changes to positive, same, changes to negative, same. Now let's look at our signs. Changes once, changes twice, changes 3 times, changes 4 times, same, same. So I'm going to have 4 possible negative real roots for a total of 7 real roots that I could possibly have. So if I'm dividing and I have 20 things to check and I find 3 positive ones, then I might as well not check any of the positive numbers anymore, because there's only 3 positive real roots. So it gives me some other idea of how to look at things. So let's see how many roots we have. Positive to negative, one change. Positive to negative to positive, a second change. Same, change, change. So we have 4 positive real roots possible. And now put your negative x in, so everything with an odd is going to change sign. Everything with an even is not going to change signs. No change, no change, one change. No change, no change. 1 negative real root possible. So it helps us out to know which numbers we should try if we don't have the graphing calculator and we have a list of how many roots to try to see if they actually do the synthetic division to 0. So this helps out. No change, no change, no change, one change, one change, no change, no change. 2 positive real roots possible. Remember, odds are going to change. Evens will not, because we're putting in a negative x, and a negative will only affect your odd exponents. Change, 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 no, no, change, change. 5 possible, 5 negative real roots possible, for a total of 7. So not only that, it takes it down to if we're looking for a positive or a negative root. So it helps us with that synthetic division when we get to it. Okay, upper bounds and lower bounds. This is theorem on bounds. Okay, so it says, with a positive lead coefficient and all real coefficients when synthetic division occurs with x minus c. If c is greater than 0, all the bottom terms during the division are non-negative, then c is the upper bound. And if c is less than 0 and all the bottom terms are alternate signs, then it's a lower bound. What in the heck does that mean? Well, let's see on the next page. So we took the equation and we did 2, negative 5, negative 6, 4. And they want you to try 1, 2, 3, and 4. Okay, why do they want you to try those? Because plus or minus 1, plus or minus 4, plus or minus 2 over 2 over plus or minus 1, plus or minus 1, plus or minus 1, plus or minus 1 over plus or minus 2, plus or minus 4 over plus or minus 2, plus or minus 2 over plus or minus 2. So your highest is positive 4, and your lowest is negative 4. So we're going to do 1, 2, 3, and 4. And then we're going to do negative 1, negative 2, negative 3, and negative 4. And this time we're not looking for zeros on the bottom. We're looking for all positives or alternating. So when I did the synthetic division here, I don't have all positives and they're not alternating sides. When I do the synthetic division here, they're not all positives and they're not alternating signs. When I do the division with 3, it's not all positives and it's not all negative signs. Alternating signs. This is all positives, which means that 4 is your upper bound. Now you're going to do negative 1, negative 2, negative 3, negative 4. And we're looking for our lower bounds. We're looking for alternate, not alternating signs. Alternating signs, negative 2. That means all my stuff is going to run from positive 4 to negative 2. So I can eliminate all the other things, all the other numbers to try that aren't between those. So negative 4 is not going to be an option. I only eliminated 1. But all the rest are options. So it at least gives you an upper and a lower bound. So let's try this one. We have plus or minus 15, plus or minus 1, plus or minus 3, plus or minus 5 over 1. Because this is plus or minus 1. So 1, 1, negative 5, negative 15. We're going to start with 1. 1, 1, 2, 2, negative 3, negative 3, negative 18. So 1's not it. 1, 1, negative 5, negative 15. Try 2. 1, 2, 2, 3, 6, 1, 2, negative 13. Getting closer at least. Let's try 3. 1, 1, negative 2, negative 15. I hope I don't have to go to 15. 1, 3, 4, 12, 7, 21, 6. Upper bound is 3. So I found my upper bound. And let's see if I can find my lower bound. I'm going to have to erase this because I'm running out of space. Okay. 1, 1, negative 5, negative 15, star, negative 1. Now remember, I'm looking for alternates this time. 1, negative 1, 0. Blew that one. 0, negative 5, 5, negative 10. Not that one. Negative 2. 1, 1, negative 5, negative 15. 1, negative 2, negative 1, 2, negative 3, 6, negative 9. Not that one. Negative 3. 1, 1, negative 5, negative 15. 1, negative 3, negative 2. 6, 1, negative 3, negative 18. Alternating. Yippee! Lower bound is negative 3. So out of my choices, which were plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Plus or minus 15 is not even an option I have to check. Plus or minus 5 I don't have to check. So I only have to check those 4, which makes life a lot easier if I don't have my graphing calculator to look at it. So upper bounds, all positive. Parts of your, when you finish, which is your quotient, or when you're dividing as your quotient, and in lower bound, alternating signs. Okay, let's put it together. Oh my goodness. Okay, let's use Descartes signs. Change, no change, change. 2, positive, real, possible. Negative 2x cubed, no, that doesn't change. Negative 5x squared plus 6x plus 4. No change, change, no change. 1, negative, real, possible. Let's do our P over Q. Plus or minus 1, plus or minus 2, plus or minus 4. And we have plus or minus 1 and plus or minus 2. So we have plus or minus 1 over 1. We have plus or minus 1 over 2. We have plus or minus 2 over 1. We have plus or minus 2 over 2. We have plus or minus 4 over 1. And we have plus or minus 4 over 2. This and this are the same, and this and this are the same. So we got 2, 4, 6, 8 things we have to check. Let's do upper and lower bounds. So 2, -5, -6, 4. Let's start with 1, 2, 2, 3, 3, -3, -3, 1. So no. Let's do 2. 2, -5, -6, 4, 2, 4, -1, -2. Hey, that was a -2. That was a negative, so that should be -3, should be -9. That should be -9, so it should be -5. Sorry. -1, -2, -8, -16, -12. Nope. 3. 2, -5, -6, 4. 2, 6, 1, 3, -3, -9, -5. Blah. 4, 2, 8, 3, 12, 6, 24, 28. Upper bound 4. So I don't have to go any higher than 4. Well, guess what? 4 is my highest one anyway. So it didn't help me a lot there. Let's get this nifty board so I can erase this. Come back and put my negatives on. I have to rewrite so much. Okay, now we're looking for alternating. 2, -2, -7, 7, 1, -1, 3. Almost. 2, -4, -9, 18. 12, -24, -20. There we go. -2 is my lower bound. Okay, so what does that mean when I use my roots? Now remember, I don't need that one or that one. Well, it means that -4 is not an option, but that's it. So 2, -5, -6, and 4. And remember, I'm looking for 2 positive and 1 negative. So as soon as I find my negative, I don't have to try any of the negatives anymore. Positive 1, 2, 2, -3, -3, -9, -9, -5. So 1 doesn't work. Let's try -1. -2, -2, -7, 7, 1, -1, 3. So they're gone. As long as I didn't make a mistake, and hopefully I didn't. 1/2. 2, 1, -4, -2, -8, -4, 0. So 1/2 is one of my reals. So x equals 1/2. So I found one of my real ones. Go back and do my negative. 2, -1, -6, 3, -3. Not going to work out, so no. 2, 2, 4, -1, -2, -8. -8 times -8 is -16. It's not going to be a 0. So that's not 1. -2. 2, -4, negative 9, 18, 12, negative 24. No. Four, 2, 8, 3, 12, 6, 24. Okay, so what happens when I only found one? Well, first thing I'm going to do is check my work. And that means I'm using my calculator to do so. Because remember, it says I can get up to 3. Doesn't mean I will find 3. Or I screwed up. And if I did, I'll go back and we'll figure out where I screwed up at. Two x cubed minus 5x squared minus 6x plus 4. Up there are some more. I got the 1/2. Should be negative 1 and positive 3, I think. 3 wasn't even an option. Ah, see, I didn't screw up. They're irrational. They're irrational. So that's the only root that I can find that's a positive integer. The other ones are irrationals. So, what do? I take 2, negative 5, negative 6, and 4, and I divide it by 1/2. So 2, 1, negative 2, negative 8, negative 4, 0. And remember, every time I divide, I lose 1 power. So this is x squared, x, and negative 8. So I have 2x squared minus 4x minus 8 equals 0. I can pull out a 2, get x squared minus 2x minus 4 equals 0. I'm going to have to use the quadratic on it, because 4 breaks into 1 and 4, 2 and 2, and they do not factor for negative 2. So, negative 2, positive 2, square root of negative 2 squared minus 4 times, I'm going to cross that out, and I'm just going to use that portion of it, times 1 times negative 4, all over 2 times 1. I could use the other portion, and the quadratic equation would get the original 2x squared minus 4x minus 8, and the original would come out the same way. So 2 plus or minus 4 plus 16, 20, square root of 20 over 2. So 2 plus or minus 4 and 5, 2 and 2, 2 square root of 5, both over 2. So 1 plus or minus the square root of 5. So x is equal to 1 plus the square root of 5. There's my positive. And x is equal to 1 minus the square root of 5. And I found my positive and negative roots. That's why you have to know everything. So I use the Descartes rule to find out how many possible roots I can have. I use the conjugate. Well, I didn't need the conjugate pair because I didn't have any i's. I use multiplicity to find out how many rules that I had. I used the rational zeros to find out what the possibilities would be for rational numbers. Now remember, it's called rational zeros, so it didn't give you irrational roots. That's why I had to do it. And then I used my synthetic division to divide it all out to come up with my answers at the end. I know. Isn't it fun? Aren't you glad that there's a graphing calculator to help us out now, rather than when I was growing up and there wasn't one? Okay, so you're going to get familiar with each of the theorems as you work through them. Make sure you take some notes, underline things, and look back at your notes while you're doing it, okay? Because this is a hard section. I wish you the best of luck.